About 4 months ago, I made a video outlining a new project that I was working on. A port of Zippy Race, the early arcade game by IRM released in 1983, to a stock Amiga 500 with just 512 kilobytes of expansion memory. The video mainly outlines some of the early development challenges I had along the way and the techniques that I used for developing against Amiga custom hardware. While I had a basic structure set up with scrolling playfields and various other systems created, it was far from a game. Now 4 months later, this is the progress I've made. We've gone from a rolling demo to a fully featured game with all these stages built in, the complete car and traffic systems, collisions. The entire game is here completable from start to finish, including the second and third difficulty loops of the game, if you are familiar with that. If we put it side by side against the arcade, it's a very faithful conversion, and I spent a lot of time and care and attention to ensure that this game was about as arcade perfect as you could get. So to summarize, Zippy Race on the Amiga runs on a standard OCS machine in 4-bit planes, that is, just 16 colors. The scrolling portion of the game runs in its own 192 by 256 bitmap for the viewport. To scroll the screen, we are using the Amiga scroll trick method by moving the bitplane pointers up the bitmap 1 pixel at a time for that smooth scrolling effect. When the pointer hits the end of the bitmap, it wraps around to a copy of the same bitmap that's stacked on top of it. So while the game scrolls, it doesn't refresh the entire screen. It only updates one row of tiles, that is 20 16 by 16 tiles for the on-screen bitmap, as well as another 20 16 by 16 tiles for the off-screen bitmap. I went into quite a bit of detail about this approach in my previous episode. For the HUD, we're using 4 16 by 256 Amiga hardware sprites, and we only update the necessary things when they occur. For example, the score, ranking, fuel gauge, and stage progress lines as necessary. Because these things don't occur every single frame, the performance hit here is negligible. In some scenarios, we use up to 4 hardware sprites to represent the motorcycle, including the collision animation when the motorcycle hits an object and spins out. But also in the 3D front view section, we're using 2 16 by 32 sprites attached, which uses a total of 4 Amiga hardware sprites 0 to 3. And once again, the remaining sprites 4 to 7 are used by the HUD. So Zippy Race, the arcade game, when you start a race, you have 5 cars on screen at once. And when a race begins, there is a round-robin spawning algorithm that runs. So for example, when the bike is accelerating, it's going to spawn cars either ahead of the bike or behind, depending on how fast the bike is traveling. The original arcade game used an IRM M52 board with dual Z80 CPUs. For this Amiga version, I've done no reverse engineering on the game at all, and I've built the traffic system mostly on feel, though I have looked at some MAME source code for some information and some guidelines. On the Amiga, each car runs its own lateral accumulator system, a value that drifts between -1 and +1. I implement this to produce smooth steering rather than instant lane snapping. Cars read from a road center cache, which is a 256 entry lookup table built during the scroll routine that maps each screen Y position to the road center's X coordinate. This is an optimal way to do car pathfinding. It also helps with curve anticipation. Cars will look ahead and begin steering before the curve reaches them, rather than react and quickly move into the curve. The car traffic system and pathfinding is pretty good for the most part. The biggest problem that I had with the cars was blitzing them on a scrolling background. Each car is a 32 by 32 image with 4 bit planes, and we need to perform cookie cutter blitz into the playfield. This sounds easy, but getting this right took a few weeks of trial and error, testing, retesting, rewriting, until I could get this to work. So in the end, I had to resort to what is known as triple buffering. Now, this is not necessarily the same thing as triple buffering that you would know on, say, the PC. Triple buffering on the Amiga means something a little bit different, and let me kind of explain it as best I can. Essentially, what happens is the tile engine draws into all 3 buffers at the same time, but the pristine buffer stays in sync with the scrolling background. Car rendering uses a 3-pass approach. Pass 1 restores the background from the pristine buffer, Pass 2 updates all the positions, and Pass 3 draws all the blitter objects. Without the pristine buffer, what we would need to do is save the background under each blitter object into a small backup buffer and then restore it in the next frame. But this causes a problem when two blitter objects overlap. Restoring one corrupts the other, and it gets even more complicated against a scrolling background. So the pristine buffer solves this completely. It always restores a clean version of the background onto the current display. So the triple buffer approach is not a new concept. It's been around pretty much since the days of the earliest Amiga games back in like 1986. But the problem now that we have is because we have three 192 by 579 by 4-bit plane bitmaps, we've basically used 1/3 of the entire chip memory on the Amiga. We've already used over 160 kilobytes of chip memory just for those screen buffers. And this is before we're talking about things like all the sprite data, all the tile sheets, all the backgrounds, all the various sound effects and music. We're talking about a significant chunk of chip memory has been used up just from those three buffers alone. And this means that we have a problem on our hands because we really have to start thinking about memory management at this point. And the biggest problem that I had once I implemented the triple buffering approach was I quickly realized I had a chip memory shortage and I had to come up with a plan to kind of get around that. Now, initially I thought maybe I would just take the L and just allow the game to run in 1 megabytes of chip memory and kind of relax that restriction. But I was adamant that I wanted this game to run just with 512 kilobytes of chip memory on a Kickstart 1.3 based Amiga as the baseline. So ultimately, what I ended up doing to make this all fit into memory was I implemented a memory management system. So initially, the way that game would work was I would load all the tile sheets and all the background data and all the sound effects and all the music data into chip memory and have them available and just, serve them up as soon as they were required. But I thought, well, I have 512 kilobytes of fast memory, so rather than doing it that way, it would be better if I created a memory management system that basically used the fast memory of the Amiga, the 512K fast memory that I had at my disposal, in order to serve up all that data during the initialization when a stage is about to start and move the relevant parts of the stage data, the asset data for that stage, into chip memory before the stage begins. So what I mean by that is we move the relevant tile sheets, the tile maps, the music that needs to be played, and the stage, city horizon, and various other assets into chip memory before the stage loads. And swapping this data in and out of chip memory back and forth between chip memory and fast memory got the job done. I was able to fit the entire game with just 512K of chip memory. This approach worked really well, and in the end, I have a total of about 60 kilobytes of free chip memory at all times, which means I can continue to incorporate additional animations and various other sound effects to the game in order to make it as close to the arcade as possible. But this also brought to light another problem that I had. Because we're copying data from fast memory to chip memory, and we are talking about a 7 MHz Amiga, that copy process needs to be as fast as possible. So in other words, we need to copy as little data as possible from fast memory to chip memory in order to serve it up. So what I ended up doing was incorporating a compression system on some of these assets to compress down those file sizes. It's a lot easier copying over a compressed tile map, which is only 2 kilobytes, as compared to one that's 30 kilobytes. The decompression system, even on a 68,000, is quite quick and only really requires a few frames in order to decompress this data down. And this all occurs between stages. So for example, if you beat the first stage in Zippy Race, there is a very slight pause here where the game is being decompressed into chip memory, and then the game stage loads as normal. And of course, this takes advantage of faster accelerator processors. If you have an 020 Plus, that decompression is going to be a lot faster than a stock 68,000. So this is a win-win across the board for everyone. Now in my previous episode, I did go into some detail about how I constructed my tile sheets and my tile maps. I used Personal Paint on the Amiga to construct my tile sheets, and I used a tool called Power Crawler, another Amiga program, to construct my tile maps. Now for the most part, this process worked pretty well, but I noticed that I had a lot of issues with it. I wanted to come up with a way to streamline this process even better. Ideally, what I wanted to do was export individual frames from MAME as PNG files, load them up into a tool such as Sprite, and then essentially copy the entire viewport onto a tile sheet, and then be able to use that to construct my tile maps. But this is not optimal because there's going to be a lot of replicated tiles. For example, a road tile, which is a single block of gray, is going to be repeated over and over again in a single tile map. So I decided that I would build my own tool to facilitate this, and this is known as Zippy. Now this is a C++ application built from scratch using ImGUI, OpenGL, and SDL3 specifically for this project, although it could be tailored to use on any other Amiga related project that uses tile maps and tile sheets. It handles the full asset pipeline. It manages tile sheets, tile maps, collision data, and color palettes. And the best part is, it uses the Amiga IFF format. The key features of this tool is a lifesaver for me. As mentioned, we can load in IFF tile sheets, we can save them. It also supports raw.io tile map formats. There is a visual collision system with lines and surface type overlays, and there's very powerful duplication detection and consolidation. Tile sheets can be compacted that removes every single empty tile or unused tile and remaps the tile map at a push of a button. You can do multi-tile clipboard pasting from tools such as Sprite. You can insert and delete rows at any position in both the tile map and the tile sheet. It also has screen boundary overlays showing 256 pixel boundaries from either the bottom of the map or the top of the map for arcade accuracy. There's even the ability to modify the color palette, remap palette indexes, also swap indexes around. You can also compare it against a second reference palette and cherry pick individual colors to maintain consistency across stages. The swap and remap feature lets you reorganize palette indices while automatically updating all the pixel data, which was essential for keeping car colors consistent across stages that use different terrain palettes. Zippy is a tool that I can't live without, and I'm so happy that I spent the time to build it out. I just found that every other tile editor out there on the market, including Tiled and various other ones, while they work really well, aren't geared for the Amiga, which is exactly what I wanted this for. Now when it comes to the Amiga, 50Hz PAL is predominantly the standard across the board. When you run Amiga games, most of the time they are built in mind for 50Hz PAL. But I live in North America, and a lot of other people that I know that have Amigas are North American as well. And I wanted to make sure that the game supported 60Hz NTSC, which means we only have a total of 200 pixels down the screen rather than 256 pixels, which means I had to make some slight adjustments to the position of the motorcycle and some other placement positions as well. But in the end, I was able to make sure that this game loads on both PAL and NTSC at either 50Hz or 60Hz. And the other thing that I wanted to make sure was the game ran at a locked 50Hz on PAL and 60Hz on NTSC. And as you can see here by using Engine 9000, a really great Amiga debugger, you can see that during the stages, we are running at arcade perfection, 50 and 60 Hz. So if you are someone that is in North America, you can run this game on an NTSC Amiga. You don't have to do any weird type of adjustments to your screen format to make it run in PAL mode. If you have an NTSC Amiga 500 with an expansion, you'll be able to play this game right out of the box. I wanted to ensure that NTSC was fully supported because, look, I love 60 Hz. I'd rather have games running at 60 Hz than 50 Hz. Now, another limitation that I had was with the heads-up display. Now, the heads-up display, as mentioned, is built from 4 hardware sprites, sprites 4, 5, 6, and 7. And each sprite shares color registers in pairs. Now, because we want to keep these colors consistent, because we basically want each of the sprites to share the same colors, we had to make them all the same. And because we only have 3 colors that we can use, this meant there were limitations in terms of some of the colors that we could have. And what I mean by that is, if you take a look at the arcade version, the high score table is in red and the score value is in brown And not only this, the 1UP text when you start a game is flashing on and off. And unfortunately, the way that we could do this on the Amiga version with 16 colors was to make them all the same color, which was white. Now the copper runs in sync with the video beam, and as the beam runs down the screen, the copper can change hardware registers at specific scan lines. So what we can do is we can say when the copper is at an exact position or an exact scan line, we can change the color registers of those particular values. So what we do here is at scan line 30, we wait, and then we set color 17 to 19 to red, which means that the high score value is now in red. And then at scan line 38, in other words, 8 pixels further down, we set it back to white for the 1UP to draw. And then again at scan line 41, we set color registers 17 to 19 to brown for the score, and then at scan line 4A, we set it back to white. Now the 1UP flash you can see here also uses the same principle. We're using a copper list to do this. We're essentially toggling the score color entries between the normal color, which is white, and black every 300 milliseconds. And this basically simulates the 1UP turning itself on and off just by using a simple copper list. But overall, I'm very, very happy with the way this game turned out, and hopefully you are as well. This was my first real Amiga project outside of doing, ports to accelerated Amigas, which even that is complicated work. It's a different type of work because you're basically porting games from the PC to accelerated Amigas and making them run as good as you can, but you're not really taking advantage of any type of custom hardware. So check out my itch.io page if you want to play the game yourself. Feel free to take a look at it and let me know what you think about it in the comments below. It is free of charge, of course, but I've definitely learned a lot from this process. I do love developing games on the Amiga. There's definitely a art form to the whole thing. It's not always going to be intuitive, especially if you're someone that comes from modern game development and going back and learning some of these concepts, learning about custom chips, learning about how to draw things and how to take advantage of sprite hardware, blitter hardware, and the copper really is just a lot of fun. Once everything is orchestrated and works well, it can be a very rewarding process. But we're going to leave it here for today's episode. Thank you so much for watching. If you liked it, please don't forget to leave me a thumbs up, and we will catch you guys in the next episode. Bye for now.